Hello guys, so today we will try to solve this CMI. It came recently in CMI. It's a part A, I mean, an objective question. So, so this is question number 10. So basically it says that M and R with the space of incrossend matrices, real matrices. Okay, as usual. So it's a space of all incrossend real matrices. So a metric is given. So like in the question, it says that view this as a metric space with this metric. So basically, so so basically, it's the actually the soup norm or the infinity norm, and from there, this metric is induced. So yeah, from there, this metric is induced. So basically, if A is something like Aij, then norm of A will be nothing but supremum ij, right? Aij. I mean, or the max, because of course, clearly, since it's a finite dimensional, supremum here will be achieved, and so we can also write max in place of supremum, right? So basically, we can actually think of MNR as like using this metric as basically Rn square with this infinity norm, right? Or the soup norm or whatever. So yeah. So now in our question, it's given that uh, so they're defining a set or a subset of this set MNR. Uh, Let U, which is a subset of MNR, which is a subset of matrices, such that so basically they are defining U this all M which belongs to MNR such that M minus In to the power n is 0. Right. So this is how they are defining U, and they are saying that U is closed, U is open, U is compact, U is neither open or closed. So like I mean from here we can see that U will be closed because so we can have a map from MNR to MNR such that A goes to right A minus In to the power n. Let's say this is an F. So this will be a continuous map, right? Since it's a polynomial map, so this will be a continuous map because, right, each component will be continuous. So suppose A is this, right? A11, A12, yeah. So um, so this will get mapped to, right? So basically, if this each component to the power n and yeah, A21 to the power n because yeah, this part is 0. And similarly, we can see that just we are subtracting one and just so this will be a continuous map. So since since each component is continuous, the whole map is continuous. So use so this is a continuous map, and we can clearly see that if f inverse 0, so 0 is a closed set. Since it's a metric space, a singleton is closed. So 0 is closed. So f inverse 0 will be nothing but u, right? All such m such that, yeah, such that, right, f of m, which is nothing but m minus I mean, identity matrix to the power n is 0. So this will be f inverse u. So from here, we can say that u is closed, right? So from here we can say that U is closed. So this option is correct, and U is neither closed nor open. So this is clearly false. Now U also won't be open because I mean since this MNR is connected, right? Since since MNR is connected, uh, yeah. Yeah, so since this is connected because, right, we can have, this is path connected because we can actually have a path, right? Let's say gamma t such that 1 minus ta sorry. So this will be plus tb, right? Where t ranges from 0 to 1. Now this will be where this will actually belongs to MNR, right? If you have two matrices, we have a path from A to B. This is a continuous map. So yeah, right. So this is path connected. So since U is closed, U cannot be open because the whole space is connected, right? So, so U cannot be open, cannot be open. So our this option is false. Now we have to check uh, uh, U is compact or not, right? And remember, this is a metric space. So, like, if I mean, it is closed. I mean, U is of course closed. Now, if U is not bounded, then it won't be compact because compact implies that it's closed and bounded, right? So, yeah. So now, uh, one more thing, right? So, so M belongs to U. Say M belongs to U, then M minus this this is 0, right? So this matrix, which we can call it by B, is nilpotent, right? So B, let's say M minus In, right? So B to the power n is 0. So B is nilpotent. So all the eigenvectors are 0, right? Sorry, all the eigenvalues are 0. So 0 0. So it has got n zeros. Uh, n eigenvalue, yeah, and all are 0, right? Now, so since each eigenvalue of p is 0, so all eigenvalue of m are basically uh, 1 1, so n ones, right? N times. So these are all eigenvalues of m. So basically, now let us try to, now since it's compact, right? So it should, since it's a metric space, it should be sequentially compact, right? So it should be sequentially compact, but I don't think it is, because like let us construct a sequence like this, right? Let's just say say we have a matrix, so 1 1 1, these are n times. This is a upper triangular matrix, where let's just take this entry to be k, and the rest of the entries, right, and the rest of the entries to be 0. Okay, so I am not writing this properly, but yeah. So we can just take this sequence of, let's say, mk. Yeah. So take this sequence such that this is mk. Now actually this is a sequence. So it's, if it's sequentially compact. So if x is compact, then it should be sequentially compact. So I mean, if and only if, but this is not sequentially compact because we cannot find a subsequence which converges, right? Because like because because like I mean simply, I mean simpler by, I mean we can simply say that like the norm, I mean of course here k is greater than 1, we are to where, okay, okay, sorry, so we have taken k is greater than 1. So I mean not yeah, yeah, of course, yeah, k is greater than equals to 1. So this is a subsequence, like, so m1 m2 m3 and something like that. I mean we can actually check, right, the norm of this will be k, right? So this will be k. So I mean we can make k as large as possible. So so u is not bounded. So u is not bounded. So u is not bounded. I mean, yeah, we can also think of it like this, right? So if k is, let's say, m2 is this 2 3 4, so we won't find a proper subsequence which converges. I mean, we won't find a subsequence which converges. So it's not sequentially compact. Or we can think of it like this, that if you take a matrix M and all put all these values to 1, and this to be some, let's say, number M, or let's say K, then yeah, this is not bounded because we can make K as large as possible, right? So if it's bounded, there will be some like M such that the norm is less than M, but we can actually make K greater than M. So this is not bounded. So this is not compact. So this is compact. So U is not compact. So only our first option is true.